What inspires you most at Zega?
What inspires me most at Zega is knowing that everybody at least interacted with Zega technology once today without even noticing.
We are the embedded experts because we have a solution for every embedded problem.
You can see us as a tool provider for other people that also make products. So if you build a house, you need a hammer, you need a drill. We are that kind of company, but for software engineers.
Debug and trace probes, production tools, embedded software and software tools. Our vision is to simplify everyday life for engineers and end users.
People using these products are developers all over the world working with embedded systems. Our market-leading J-Link debug probe is the one piece of hardware that you will find on every embedded developer's desk.
Zega technology is inside everything. Space research, medicine, robotics, motorsports. You can find Zega everywhere.
With our technology, I hope we make people's lives better or easier.
My main motivation is seeing all these projects come to life and change the world or improve the world. Zega is the professional home for so many different people.
Developers, makers, engineers.
What unites us all are three words.
It simply works.
Test. Yep, it's good.
Welcome back, everybody. I see you got coffee and are excited for our next talk, Compiler Black Box Testing and Peculiar Bugs Encountered by Ahmed. Enjoy.
So, good morning, everyone. Sorry, I'm still getting to this adjustment. Welcome to our presentation. Today I'll be presenting Compiler Black Box Testing and Peculiar Bugs Encountered. I'm Ahmed Ibrahim from Solid Sands, and I'm joined by my senior colleague, Nicola Rossi. So first I'll present quickly who we are and what we do. But first and foremost, I'll introduce myself. Let me take this. Yeah, here now should sound better. So I'm a software engineer that's primarily involved with C and C++ every day in my work life, which is good because it gives you like a daily roller coaster of emotions, keeps me passionate about things. And I did a bachelor's in computer engineering, and then I did a master's of software engineering from the University of Amsterdam. And then I joined Solid Sands. So about Solid Sands, for those who aren't familiar, we're a Amsterdam-based software company specializing in compiler and library testing and qualification. So every day we strive to improve the quality of C and C++ compilers, libraries, and analysis tools while enabling their safe and secure use. We also provide services to companies in the semiconductor, compiler, and security industries, as well as safety critical companies in the robotics, automotive, railway, and medical industries. And we have two primary products, SuperTest and SuperGuard. And to reach the bugs, the peculiar bugs we're about to share with you guys today, we have been primarily making use of SuperTest. And SuperTest is our C and C++ test and validation suite. So it's mainly used to test the compilers and standard libraries conformance to the ISO C and C++ specifications. And as you can see, it's supported by a wide array of C and C++. It supports a wide array of C and C++ versions. And to do so, to test this conformance, it has a comprehensive test suite that has both handwritten and generated test files. And these test files not only test the compiler's front end, but it attempts to test the compiler as a whole. So think of the front end, the back end, the different levels of optimization passes, as well as code generation. Now, in our line of work, we can come across all types of bugs while doing all these daily compiler testing. And whenever that happens, we try to find the root cause of it. We dig deep a bit, and sometimes we find that it's the result of an ambiguous concept in the C and C++ standards. And there we really have to take a second and third look, sometimes even a fourth and fifth, because these standards can get super ambiguous, right? But other times it could be a misstep in the development process, which we quickly address. Other times it could be a shortcoming by a particular compiler. And more rarely, it also could be a shortcoming by a particular component in the compiler's toolchain. So for today, we have 6 bugs that we thought might be interesting that have been judged to be shortcomings of compilers. And they will all be in C++, so none of them will be in C. And we'll obviously take any questions at the end after we present them. So just as a disclaimer, right before we start presenting the bugs, I just wanted to be completely clear how appreciative and deeply grateful we are to the GCC and Clang communities. Their constant hard work and dedication truly make the daily lives of us as compiler testers much easier. And by presenting these bugs, this is in no way an attempt to critique these amazing open source projects, but it's more so an attempt to highlight the importance and added value of having a validation suite when it comes to the detection and eventual mitigation of bugs similar to the ones we're about to present. So to begin with, in the first bug, this test file will dissect 2 slides later, so for now let's keep the focus here on the right-hand side. And one of the commonplace programming techniques in C++ is what's often called RAII, which stands for resource acquisition is initialization. And basically what this principle states is that you, as the C++ developer, if you use classes to manage your resources in a correct manner, so you use constructors to create them, destructors to destroy them, and so on, the language in turn will make sure to correctly allocate and release these resources in a manner which guarantees no leaks take place in the memory space. So you can think of it as a contract laid out. You know, I use classes correctly to manage resources. The language will make sure that these resources are allocated and released in a time. With that being said, let's take a look at a segment from the C++ standard, which states that if we have an object whose initialization or destruction has been terminated by an exception, then it will have the destructors executed for all of its fully constructed sub-objects. So when an object gets terminated by an exception, everything within it should also have their destructors called. Now, recall this earlier code file. We're going to split it up in 3 now, 1, 2, and 3, and then check something that has very much to do so with this clause right here. And so to begin with, we have a global variable called a, which is initialized to 0, and we're going to use this global variable to track the instances of my class right here throughout a program's lifetime. So whenever an instance of my class is constructed or created, A is incremented, and whenever it's destroyed, it's decremented. So ideally, by the end of my program's lifetime, A should be set to 0 in an ideal world where no leaks took place, right? And then we have 2 functions here, f1 and f2, and they're expected to return an object of type myClass. Function 1 does return an instance, but function 2 throws an exception. right? And we have a class here called class X that has two objects of type myClass. And then we have an empty function, which is conveniently called function. And it has no body, but it takes as an argument an object of type class X right here. And let's take a look at this try and catch block right there in the middle. In the try segment, we call this function, which takes X as an argument, with an initializer list, which has both functions, f1 and f2. And this function right here will attempt to create an instance of the class myX with these initializer values. So essentially what takes place here through this aggregate initialization is that the return value of f1 will be assigned to obj1 right here, whereas the return value of f2 will be assigned to object2 right here. Now, when this function is called, we create an instance of this class right here, class X. So its constructor is called, which is good. Now, recall that A is only affected by my class. It's not affected by class X. So class X's constructor is called. That's good. Now we go to the first assignment, f1's return value being assigned to object 1. That will actually take place because function 1 returns an instance. So now A is incremented because this is my class. So now A is at 1. Now towards the second assignment, the return value of f2 into sub-object 2, or what is called here obj2, this one will throw an exception. And by virtue of this exception thrown, we will immediately head to the catch block, to the catch segment of this try and catch block, and where it does a cval verify basically functions as an assertion. It will just check that exception has the value of 13, which is true, it does, but this is not very relevant to what we're doing. So let's go back a bit and see what took place here. We had an object of class X constructed, good. We had a sub-object 1 right here constructed, good, A is at 1. But then the assignment failed by virtue of having f2's return value assigned to object 2. So object 2's constructor was not even called, and because an exception was thrown, the object of class X's constructor has immediately its destructor called because an exception has been thrown. Now, recalling from the standard that every fully created sub-object, which in this case object 1, it had a successful creation, should also have its destructor called, at which point we will end up with A being decremented and A ending at 0. And this is actually what took place following this bug being fixed in GCC 12. So if you take a look here at GCC 11.4, which was released less than a year ago, A was still at 1. It was not at 0 as we expected to be, which indicates that not every fully created sub-object was destroyed by virtue of this exception taking place. And to recap this initial bug, it's prior to it being fixed in GCC 12, it did pose a serious language security risk by having a resource leak into the memory space, which was this obj1 right here. So, moving on to the second bug. One thing I want to note really quickly, so it has to do with the versions of standards that I quote. So whenever I quote a clause or a requirement from the C++ standard, I'm trying to bring the earliest instance at which it was included where it's like provided with clarity. That's not to say these don't exist anymore or nothing. All of the clauses or requirements that we'll discuss today are still present up until at least C++ 20. None of them have been deprecated or anything, but perhaps their syntax just changed a bit or so, but the core essence is still there. So for the second bug, it states that the type of a floating literal is a double by default, unless it has a suffix attached to it. So if you see a floating literal such as 0.8 or 1.9, it should be regarded as a double by default, unless you find an F after it, at which point it would be a float, or an L for a long double, and so on. So if you take a look at A1 and A2 here in this code file, A1 is 0.4 without a suffix attached, so by default it is of type double. And then A2 here is the exact same value, but it's explicitly casted with a double, which in this case is somewhat redundant because A1 and A2 should be treated as double, explicit cast or not. It doesn't matter for the right-hand value. And if we try and perform an assertion for equality, mind you, these are two identical values. Up until the latest version of Clang, that was indeed the case. Prior to the latest version of GCC, that was indeed the case, because thinking of it, it's just the exact same identical value being represented from double to long double, so there's only one way for this to take place. But in the latest version of GCC, you get A1 equals 2, the assertion fails. And what appears to take place is that there's a discrepancy in the representation of the exact same value when it gets assigned more bits to fit into long double. And in this case, A2, which was explicitly casted to double, has the original 64-bit representation that we see in other versions, but for some reason A1 seems to be represented with more accuracy, perhaps that of 80-bit or so. And this discrepancy, which might initially seem somewhat harmless, can actually evolve into a big problem. Think of a large code file with multiple arithmetic operations, which involve variables that take an explicit cast, at which point this can become very troublesome. It's just the unpredictability of it in arithmetic operations. Moving on to the third bug. This one involves the utility of the STD hash specialization for Boolean vectors. Now, in the standard, it states that there is no requirement that the data is to be stored in a contiguous allegation of bool values, but they do recommend a space-optimized representation. So by virtue of this recommendation, it would be very common for you to find the Boolean vector represented as bits instead of bytes, as associated with other data types apart from Boolean. Because all you need is one bit, really, 1 for true, 0 for false. And this is a time and space efficient implementation, which is recommended but not enforced by the standard. But also there's one more thing that's not enforced by the standard, and that is the STD hash specialization for the Boolean vector. So not only how a Boolean vector is designed, but also how it should ideally be hashed, or how to get a hash value out of its functionality. And if we take a look at how it is in Clang, if we take a look at LLVM's implementation of it, we can notice a problem that might arise. So let's dissect it bit by bit right here. The colors are a bit faded, but I hope they're better in the middle screens. But here we have a variable called h, which is initially set to 0, and h is actually the hashing value itself. This is what this functionality will return at the end as the hash value when you give it a Boolean vector. It's initialized to 0. We also have another variable called n, which takes the size of the entire Boolean vector, recalling that it is represented in bits, so a Boolean value for each bit. So if we have a Boolean vector with 70 values, then n would be 70. And then what happens is that it splits the Boolean vector into chunks. These chunks are called words. Now, about their size, how many bits fit in a single word, this depends on the environment. For the sake of this test, we are operating in a 64-bit environment, in which case there are 64 bits per word. Had we been in a 32-bit environment, there would have been 32 bits per word. And what it does is it assigns a pointer to the beginning word, to the starting word, and then it moves word by word, and effectively all it does is performs an exclusive OR operation with this, starting with the hash value, which was initially set at 0. So if we have, in a 64-bit implementation, if we have a Boolean vector 128, that would be 2 words, so it would effectively perform 0 for word 1 exclusive OR word 2. And then there's this segment right here, which has to do with partial words. And for the sake of our example, we will not go into this, but a partial word would be if we have a 70-bit Boolean vector, for example, in a 64-bit environment. We have one word from bit 0 to 63, that's good. But we still have extra bits at the end, and these would constitute a partial word, and these would get masked so that they do not affect the exclusive OR operation. Now, let's say we have 4 Boolean vectors, A, B, C, and D. We're going to populate A, B, and C, but we're going to leave D as is. And then at the end of things, we're going to check if the hash value returned by the std hash specialization of A is unequal to B, and so on, to make sure that it functions as expected. And for GCC, up until the latest version, it actually does. You get unique hash values when you populate a Boolean vector, but if you leave it unpopulated, you get a 0, which is D right here. But in Clang, which we just saw the implementation of, something interesting happens in the case of repeating, if you have in the case of having a Boolean vector with repeating patterns. So let's take a look here. We have this for loop. It runs for 64 iterations, and in each iteration it's pushing in a repeated pattern. So in this example it's false true, so think of it as false true, false true, false true, and moving on. Same thing with true false, same thing if it's all true or all false. These are repeating patterns, and if these are perfectly fitting within a word, so here it's 64 iterations times 2 Boolean values, we'll end up with a Boolean vector that has 128 bits, which is 2 words. When it performs, by virtue of associativity, look at it here. If you say this x right here is the 0 that we began with, and then we have 2 words exclusive or one another, and they are identical, because this repeating pattern from bit 0 to bit 63 will go like false true, false true, false true, and then from bit 64 up until 128 it will go, sorry, 128, yes, it will go false true, false true, false true again. So we have 2 identical words, and any exclusive OR operation on an identical value gets you a 0. So if you take a look at this operation right here, it's essentially performing an 0 exclusive OR with 2 identical words, which can be considered the same representation here. Let's say it's y, and then we will be effectively doing 0 exclusive OR 0, and we end up with 0. And that's why this can seem freakish at the start. It's like I just populated an entire Boolean vector, and then I get the hashing value of it as 0. And this is not just with, this can be reproduced or replicated in 2 manners. The first is having any even number of words which have repeating patterns, but not odd ones. Because thinking of it, if you have 2 words, yeah, they'll cancel out 4 words and so on. But if you have 3, actually, 2 will cancel out, and 1 will be taken with the initial 0, and then you'll end up with a unique hash value. So one case of reproducing this is even words of the repeating pattern. Another is having the repeating pattern perfectly fit within, in a 64-bit environment, within 64. So here we're repeating 2 bits, and 2 goes into 64, same as 4, same as 8, same as all of the factors of 64. So in case these also fit perfectly within a word, then they're repeatable. Then you'll also get a 0 from Clang's hashing value now. Upon initial inspection, this seemed like a crystal clear bug, but upon closer inspection of how it's actually implemented, one could argue it's more so of a weakness than a bug, but one that can be exploited if you're not aware of it. So the implementation-wise, actually, if you take a look at this implementation and you recall that it needs to be time and space efficient, it's actually a good implementation to perform just that, but it does have a low collision resistance. And as a result, it wouldn't really be a candidate for cryptography or safety-critical applications and so on. Now, moving on to the 4th bug. In the C++ 17 standard, states that an expression is a core constant expression unless it has one of the following. Actually, the list goes on and on, but I just stopped here. Because in 2.6, it has an operation that would have undefined behavior. So if you have a constant expression, in the evaluation of it, there's undefined behavior. This is not a core constant expression, it nullifies it. So let's take a look at this code file right here. We can explain it pretty quickly, but we're trying to reach n_dist. This is the expression we're trying to evaluate, essentially. And to reach there, let's take a look at what's here. We have a struct n. It has 2 member arrays of const char. They're both of size 2, m1 and m2, and it has a constructor that gives them values. So we create an instance of this struct right here by virtue of the small case n. And then we have two pointers, one that points to the beginning of M1 and another that points to the beginning of M2. And then we're trying to perform pointer arithmetic with them in this const exp and dist. So the C++ standard allows pointer arithmetic within the same array or one element past the end of the same array. However, trying to do pointer arithmetic including subtraction between two different arrays is actually what constitutes undefined behavior. So PM2 minus PM1 right here has undefined behavior. And as a result, this nullifies the status of n underscore dist as a core constant expression. And the latest version of Clang actually reflects that correctly, and it says right here, actually in this very dark black void, it says note, but because of the contrast, you see nothing. You see, yeah, you can't see anything. But it says note, subtracted pointers are not elements of the same array. But surprisingly, the latest version of GCC compiles it without complaint as if nothing has gone wrong. And it actually even gives a value of 2, which if M1 and M2 were contiguous in the memory space, then it would make sense to have 2, because the pointer to the first element is 2 away from the pointer of the second element, given they are contiguous. But keep in mind, there's no requirement that this takes place or that this is always replicatable. I just invented the word replicatable. So to recap this bug, yeah, I just recapped it pretty well. So no need to further recap. It's just the latest version of GCC allows it and gives a value, whereas this is not a core constant expression. You should get an error for it. Now moving on to the fifth bug. It states there. Let's take it from the beginning. C++ 17 introduced a logical operator type trait called conjunction. And conjunction takes a list of type traits. So think of is integral, or is floating point, is enum, is aggregate, whatever. It takes a list of type traits, and it checks them for a member called value. And once this value is convertible to bool, which it actually enforces, every single type trait in the list or argument shall have a member called value, and it shall be convertible to bool. Once it does that, it performs a logical AND on the entire list. So if we have multiple type traits and they all have a member called value, and let's say they're all true, then conjunction's value returns true. If one of them is false, by virtue of having a logical AND, then it will return a false value. It actually has two members. This logical operator type trait has value and type, but for now we're focusing on value. How it inherits the type is a similar story, but it doesn't have to do with us right now. So let's take a look at this code right here. We have an empty struct called A, and we have a struct called not convertible. And this struct right here, not convertible, has a member called value. It's of type A, and it's initialized with a temporarily instantiated object of the struct, the empty struct. And so it has a member called value, which is good. That was one of the requirements. And the other one was it has to be convertible to bool. Now, this empty struct right here does not have a conversion operator to Boolean. As a result, this value is not convertible to bool, and we can do this by performing an explicit cast of bool to this value right here with a non-convertible. And what we'll see is that both GCC and Clang agree that this conversion cannot take place because const A cannot be converted to bool without it having a conversion operator. So now we've established that this value right here is not convertible to bool, which directly opposes the relevant clause of the standard we just depicted. Now that we've done this check, let's comment this part out, right? Let's forget we saw this. And in this file right here, we have it already commented out, and then we're trying to access the value member of conjunction, which returns true if every type trait within it is true. But then we pass the not convertible struct as one of the arguments. And it does have a value, but it's not convertible to bool. And surprisingly, in both Clang and GCC, we do not get any warnings or errors that something misplaced has occurred. And yeah, this is on both of them, so this isn't a single implementation thing. And you can even put it in a list with other type traits, and it will still not complain. As for what the value it returns and so on, it can return something arbitrary, but in any case, this should not take place. This should not be accepted, since it's not convertible to bool. Now onto the sixth bug. I had to take my glasses off so I could see, because this was interfering, and as a result I have very bad eye vision, so the people in the front 3 rows I was staring at expeditiously throughout the whole thing, and now that I actually see the people behind them, I see the difference in reaction, because I was staring at these people, so I'm so sorry about that. Now onto the final bug. It states that in the C++20 standard, it states that an explicit instantiation of, and then it gives a function template, member function of a class template, or variable template. For now, we're only concerned with the last one, variable template. So let's reword it like this. An explicit instantiation of a variable template shall not use the inline, const exp, or const eval specifiers. So these 3 specifiers are forbidden by the standard to be used. And we can give a quick test about this. Right here, if we use if we create an explicit instantiation of a variable template is void underscore v, and this essentially returns the value, a Boolean value of true if the object right here is void and false otherwise. So this explicit instantiation makes use of the keyword const, which wasn't one of the 3 forbidden ones right here. So it's permitted and it compiles as expected, as you can see on the left-hand side. Now, moving on the right-hand side, we have the exact same snippet as on the left, except we're using the const exp specifier, which was one of the 3 forbidden in the C++20 version. They were inline, const exp, and const eval. And GCC correctly points out in the latest version that explicit instantiation shall not use the const exp specifier. However, the latest version of Clang does not complain, and it allows it. So this is a more straightforward one. This, I believe, could be a discrepancy on GCC's side. Sorry, discrepancy on Clang's side. Sorry, GCC performs as expected. Clang does not. So that was about it for Clang, and that's it. Any questions? Was my voice clear throughout this? Okay.
For bug number 5, does it only happen if you don't use the value?
Does it only happen if I do not use the value?
Yes.
No, I believe so, yes. Okay. I'm under this impression, yes.
So the optimizer just optimizes it away before it checks it?
Before it checks for the inherent type of value, yes. We even checked for the value itself, and sometimes it does return true type or false type arbitrarily.
So you showed us a lot of the horrors of C++, and
I showed, sorry?
You showed us some horrors of the
Yes,
C++, etc. So what are, let's say, 2 tips you can give to us to avoid such traps? Because I think a lot of people trust in GCC and Clang to not fall into this fall pit.
Trust me.
And the second tip?
We have another product called SuperGuard, but it's not related to this. It's not related to this. No, this was mainly a highlighting of the importance and added value of having a test suite. Like I said, a validation test suite. So you can't blindly trust. Trust me, the standard gets extremely ambiguous at times. Sometimes you read a single statement and you stare at it 20 times, struggling to understand what they're trying to say. And you can't really put the blame on the Clang and GC communities because they're also doing their best. But you cannot put blind trust into anything. That's why it's important to have a validation suite. Yeah. I know a good one called SuperTest. Yeah, if you remember.
Have you ever tested ARMCC and its library? And if yes, how bad was it?
ARMCC. Well, you can take this question. You can take this question. Yes. ARMCC, have you ever used the ARMCC compiler and how bad was it? Okay.
ARMCC, we tested ARM. I don't want to see that something is bad or good because it's a work of people, so it's not nice to say they have done something wrong. So it's as we say, thanks to the community to the product developer that they done their work with the best effort that they done. So we cannot say that something is correct or it's bad or not. And also we should understand that nothing is perfect. So then we should mitigate the error that can be in these things. This is our goal: mitigate what can be, what we can find in a product.
Any other? Yeah.
Firstly, awesome stuff. I was just wondering, what is your process of defining the use cases? Because, like, are you actually looking into libc++, libstandard C++, GCC implementation, or are you going through the standard? What is your process of defining the use cases? And yeah, that's basically the question.
Well, first and foremost, we go through the standard. First and foremost, our strict scripture is the standard, right? This is what we consult first and foremost. From the standard, we perform our own requirements-based testing, depending on what we comprehended from the standards clauses or requirements. That's why I said some things are ambiguous and it takes more than one time. A somewhat like relative indicator of a test for that, to reach that, we can use GCC, we can use Clang, but they are not what dictates what a good test is and what isn't, but they can provide you of an indicator. So when we do that and we find them that they are both in agreements, we can test it for further compilers, and then we always do manual inspection in any case of all the tests, and then it provides us with somewhat of confidence. But then when we find some blatant discrepancies, we think it's interesting to share. We say, oh well, this one did not run on Clang. And then I ask another developer, what was this one? What happened here? And then we launch this process, and then we find out. Sometimes it's shortcoming on the compiler side, but there are shortcomings on other sides. But these are the ones interesting to share, right? Right.
How much of the standard library do you actually test? So I've seen that you not only test freestanding, but when it comes to the concurrency support library, like threads and mutex and things like that, it's probably more an operating system test than a compiler or library test.
Right. So an initial question was how much of the standard library is being tested. That we split into headers, and it's relative to what clientele also ask about headers. So it's not like we can go from page 1 to the last page and cover every single header in there. But regarding concurrency, mutex, and so on, Nicola can give a better answer.
Hello?
For concurrency.
We test that it's present the functionality, and about the proofing or modeling, yes, it becomes a challenge that we are facing now, but we are in a good point on that. About the library, we have in the important things we have 100% coverage, and also MCDC level MCDC coverage we have quite good value, and also depends on your implementation. So maybe because we test with some implementation and we have a good level. Maybe your implementation has some particularly tricky for do the things, and maybe we didn't cover. But if we have an implementation, we can see.
Are there? Yeah, there's another question.
So an additional question to the do you go through the standards? Do you also go the other way, go through known bugs of, for example, Clang and GCC, and check if you can find those as well for older versions of them? Or
Can you repeat the question? Because I think you started the question with both standards. Which two standards?
It's in addition to the question from before.
Right.
So do you also go through known bugs of older versions of GCC or Clang and check if you can find them? So do you verify if the bugs that have already been found are found by your tool as well?
If it happens that we come across a bug, then we can perform research or exploration to see if it has been already persistent in an earlier version or so on. But we do not actively scope the earlier mentions of bug reports or so on, if that's the question. We do not, no, we do not dedicate this time for this.
Okay.
So essentially, no.
Thank you so much for answering all that questions. Are there any left?